like to, I'm thrilled actually to tell you that I'm going to meet Vanessa supervisor. You remember last time we met Vanessa and we were supposed to meet Dr. Andro, but we were very very lucky actually to have Andro supervisor himself, Professor Bruce. Professor Bruce is, I will tell a little bit about his background. One of the very smart scientists in Stanford University here. He did his PhD in UCLA, University of California, Los Angeles, and he did his postdoc his postdoc in Lawrence Livermore National Labs, and then he worked there as a physicist before he became a professor in Stanford University, and till now. So he earned the Newcomb Cleveland Prize, yeah, one of the prestigious prize in USA, by the American Association for Advance in Physics. So he's well known in this field, and he's the principal investigator for the Gemini planet imager. And so I'd like to welcome him in your behalf, and welcome Professor Bruce, and thank you very very much for giving us this chance to talk to you.
And thank you for the opportunity to talk.
So I let you talk about your research, maybe some details for people.
Yeah, say a little bit about my field. I'm a professor in the physics department, but I'm really primarily an astronomer. So I work on studies of celestial objects, and also, maybe more than many astronomers, I work on the technology that enables us to study astronomical objects. And so within that, my particular science focus in astronomy is the study of extrasolar planets, so the study of planets that are orbiting other stars. And as most people know, there's 8 or 9, depending on how you count, planets in our solar system, and that's all there was when I was a graduate student. But now we know about 2,000 planets that are orbiting other stars, and astronomers as a whole are trying to understand the frequency and nature of planets orbiting other stars, how common they came from. It turns out most of these systems are very different than our own, and with the kind of ultimate holy grail of answering the question of whether there are other planets like Earth out there, whether there are other planets that potentially could or actually do harbor life.
And so these stars are in our galaxy here.
Yeah, we right now we can only do this for stars that are pretty close to our sun, within a few hundred light years at most. So stars in our galaxy, but separate from our own solar system.
So what type of information do you provide to the, let's say, the astrophysics community? Like, is it the number of stars, or the content of these stars, or the planets?
Different people do different parts of it. What our group focuses on is some people do statistics, what fraction of stars have planets, what the radius of those planets are, things like that. What we actually do is we see the planets themselves. We figure out ways to, planets are small, stars are big, so planets are a million or a billion times fainter than the star that they're right next to. So we work on technology to block the light from the star, clean it up, and then see the planet separately. And if you do that, you can then take the light from the planet and feed it into a spectrograph and measure its composition. So we do the atmospheric composition, the temperature, and the nature of planets.
So by just looking at the images and do some analysis, you will be able to tell what the composition of that planet and the atmosphere looks like.
With the technology we have right now, we can only do that for giant planets. So for planets like Jupiter, the biggest planet, equivalent of Jupiter, or even bigger, the biggest planet in our solar system, we can't see the Earths. But even those provide clues to how they formed, whether they formed out of solid material like the Earth did initially, or gaseous material. And the hope, the end game of this, maybe 10 or 20 years from now, is with more sophisticated telescopes in space, we'll be doing the same thing for Earth, so that we'll get the spectrum of a little blue fuzzy dot in an image, and that spectrum will show oxygen and water and chlorophyll and ozone and all the things that we associate with life.
And can you tell just briefly, like, what kind of technique, what exactly you do in terms of science?
How we find them.
How you find them.
So that fades into the technology side of this. So I do this mostly with large optical or infrared telescopes on the Earth. And if you're on the Earth, there's air between you and the stars you want to look at, and the air is full of turbulence that blurs the image of the star and hides the signal from the planet. And so I work on a technology called adaptive optics, which involves sensors that can measure the way the turbulence in the air has distorted light, and then mirrors that can change their shape 1,000 times a second to bring that light back into focus and correct for the distortions. And in principle, you get images as good as the Hubble Space Telescope, except you get them from the ground, where you have even bigger telescopes available to you.
So the correction is based on the intensity or fluctuation, or the travel, the wave, how long it travel?
We actually sense the whole wavefront of the light, so we take the wavefront of light and feed it through an interferometer, or in our case it's a thing called a Shack-Hartman wavefront sensor that's a geometric wavefront sensor. So we measure all the rays of light that have come from the star we're looking at. We measure how those rays have been distorted, and then use that to command the mirror back to make the image sharp again.
You mentioned using MEMS, I think, right? MEMS, is it MEMS?
One of so the mirror that can change its shape can be made with a bunch of different technologies. Sometimes they're simple glass mirrors with piezoelectric surfaces, but sometimes they're silicon MEMS, microelectromechanical systems.
So do you have like a specific size for these detectors, like large or small?
One of the reasons we like the conventional mirrors tend to be big, like this big, and then if you're building an optical system around it, that means your whole optical system is huge. The MEMS mirrors have the advantage of being relatively small. So a MEMS mirror might have 4,000 little individual actuators, places where it can bend in an area about this big.
Can you tell them what exactly MEMS does?
So MEMS stands for microelectromechanical system, and it's basically like a silicon microchip, except that it can move. So it's made the same way we made silicon microchips, but with tiny little pieces of silicon that can bend or respond to electric fields and cause them to distort and change their shape. So we can send electric signals into this, and the top of this silicon mirror will bend itself up and down by a few millionths of a meter, a few microns, but that's enough to fix the effects of the turbulence in the air.
So, okay, that brings me back to my question, and so the correction of this image, is it based on the intensity of the light when it changed because of the atmosphere, or what exactly happening there?
It's really it's hard to do this without a diagram, but it's really you're an optical scientist, so it's really the whole wavefront of the light. So we collect the light with the telescope, the light comes in. If you think of light as a wave, which is not a bad way to think of it, if there was no distortions, it would be nice flat parallel waves coming in. Because they're distortions, the wave is bent and crinkled in various shapes. And with our sensors, we can measure not just the intensity, but the slope of that wavefront at a whole bunch of different locations. And then you take that slope information and turn it into an estimate of the whole wavefront, which is like an integration process or a least squares process. And then that changes the shape. So we're actually measuring the real shape of the wavefront of the light with one technique or another.
So how do you know that your correction is correct? Is it because you have, let's say, most of the images gives you this information, and then you say, okay, these are errors?
What we usually do is we usually split the light. So we'll take one wavelength of light to measure the wavefront, and the other wavelength of light we make an image with. And the atmosphere is very achromatic. It does the same distortions at all wavelengths, so that works. If you're looking at a point source like a star, you know that all a star can do is make plane waves. And so if the wave's not a plane wave, then you know it's distorted. These techniques actually will work even for objects that aren't point sources, and that's more complicated. But yeah, the wavefront of light from an object has to be flat by the time it's propagated across the universe to you. And if it's not, then there's a distortion and you fix it. And you can usually do this. If you have, so downside is you need a bright star to do this. You have to do this every millisecond or every 10 milliseconds. So you have to have enough photons to make that measurement in 10 milliseconds. And bright stars themselves aren't that interesting, except to me, because I want to look for planets around them. If you have some galaxy you want to look at, galaxies aren't bright enough to do this. But if there's a star right next to the galaxy, they both pass through the same atmosphere, and so you use the star as a reference for the galaxy. Or other people, not myself, but other people who work on this technology, can actually use lasers to make an artificial reference beacon high up in the Earth's atmosphere at about 100 kilometers. And then you put that bright laser beacon next to the faint galaxy you care about. And the wavefronts from both the laser beacon and the galaxy pass through the same pieces of air.
So that's a reference for you, basically.
It's a reference, yeah. We don't do that because what we're looking for are planets orbiting stars that are close to the sun, and stars close to the sun are bright anyway, so we use the star itself as a reference. And then the planet next to it gets sharpened up as well.
But, image processing technology is really, really advanced now, and it uses machine learning and artificial intelligence. And are you implementing these techniques in the?
We also apply, so you can't do this just with image processing because of the way the noise propagates through the system, that the turbulence is so bad it doesn't erase all the information, but the signal to noise of the information is so low that if you looked at it with a real detector, you'd never be able to reconstruct what was there. But we do apply image processing afterwards to
probably will have enough data to train your algorithm that using some healthy cells, let's say, which the things get distorted, and then you can use that as a training set for your.
Things like that probably, we'll talk about them, might work better in other applications. So one of the things I do is try to use the same technology for biology and microscopy, we can talk about in a few minutes.
Yes.
But for the astronomy case, because you have to make the measurements in a millisecond, and because images lose information compared to wavefronts, it's almost impossible to do this without some kind of sensor, without some kind of wavefront sensor. We can't measure the phase of light directly, we measure the intensity of light, and in an image that means you've lost information about phases. You can, like, if you look at an image that's out of focus, you can look at an image and say it's out of focus, obviously, but you can't tell just from the image, is it out of focus this way or this way, because they look identical.
Right.
And so there are a lot of those degeneracies when all you have are images that you can fix with a sensor.
Okay, two questions, two more questions. The first question is, how do you tell there is, let's say, the composite of this plant? How do you extract this data? Do you have already a reference somewhere or database, and then you fix a spectrum to it, or how do you distinguish that?
That's basically the idea, that we would look at the spectrum and then look for the signatures of particular elements or molecules present in it. So we commonly see carbon monoxide, for example, and either from laboratory experiments or from theory, you can calculate what the spectral lines associated with carbon monoxide at 1,000 degrees Kelvin should be, and then see those lines present in it.
The last question, second to last question.
Yeah.
We know that the dark matter kind of bend the light, and so maybe you're receiving different information. Do you suffer a little bit from this, or do you have any technique?
The stars we look at are so close, there's no dark matter between us and them for all practical purposes. Dark matter matters on the scale of galaxies, not on the scale of neighboring stars, which is good. Life is complicated enough. Atmosphere in the way, let alone all the dark crap.
Right. So I can see that you have really huge passion for doing science. So there's a question I always ask people who are doing science, and ask them, why you chose to stay in academia? Well, if professor like you, if you go to Google or I don't know, Apple, or you will get a really well-paid job there.
Yeah, they're not looking for astrophysicists. So at this point in my life, it's a more complicated
I don't think they look at the astrophysics itself, but they look at the skill he has. So what kept you in academia?
It's only a slightly different question for me because I moved to academia. So I was at, as you mentioned, a U.S. government research laboratory for 20 years, and then only 3 years ago did I decide to come to Stanford. And there are a couple of reasons I did that. So obviously you don't make $1 million working in a U.S. government research laboratory either, but it was a more focused area. Partially, there's certainly an element of coming out to Stanford to want to try and make a difference. And so one of the things I'm trying to do is, one thing you can do at a university is work in a lot of different areas. And so I'm looking for the opportunities to connect the research I do to biology and medicine. I wanted to get involved in policy and in sort of discussions about science policy and climate change and things like that. And having the seat of being at a first-class university like Stanford means people take you seriously in a way that they don't in other areas. So I wanted to be able to say to my daughter when she grows up and the planet's 3 degrees warmer and she asks me what I did, and I say, well, I found some other planets, did that help? And no. So I want to be in a place where I can at least have some influence on bigger questions and bigger decisions, and a university is one of the paths to doing that, as well as through teaching. It was.
If you ask me, we're talking about policies now. If you ask me, yes, we have a nightmare government, which we don't like at all. Not all of the people don't like it, to be honest. But I think Sudan isn't sanctioned by US government.
Yeah.
And this sanction is not from now; it's from since very long time.
Yeah.
And unfortunately,
we're not very good at that.
Yes, I agree.
Inertia.
You
Yeah,
are not
settles in.
good at that at all. And the problem is that you think when you put sanctions, then you're putting pressure on the government, so it change, or putting pressure on the people to change. It happens opposite. One of the causes for these were the sanctions, and this is what I believe myself. So to resolve this issue, it's not about, let's say, first of all, let's look at the sanction effects or the side effect of this sanction. First, we can access to medical, let's say, equipment or medicine advanced technology at all. We cannot use that. So so we are left ways behind in medicine, and we have horrible situation in our hospitals because of that. That's one concern. Second thing, as a scientist, a physicist, I tell you, we cannot buy nanotechnology equipment, which we can be used, as you said, just mentioned now in medicine. So we can get advanced education. And sure, if I propose for a cold atom center in Sudan, they will I might end up in Guantanamo or somewhere. Right?
Right.
From my point of view, the best solution is not sanction, but it's actually to elevate the democracy, help people to do a fair election. Do a fair election. Lots of people, they don't like the government and they won't hesitate to vote against the government if we get a fair election which is monitored by international community. Why you don't do this? Why is the government? Why Obama doesn't do this?
It's a complicated world, unfortunately.
So I think that that's from my point of view how we get settlement in democracy in Sudan. And once that's happened, you can imagine what happened in investment in that country.
I think that's right. Yeah, that's again the analogy to Chile. That ultimately, when it settled into being a democracy, it was much easier for people to make investments and
Exactly.
make commitments to scientific research.
If you're an investor from USA and you want to invest in Sudan, you might more likely to get a job. I'm not discouraging you, but just to show you how much is.
Think about it.
All right, then I want to ask you last question about Sudan, still Sudan. So if we want to build, I guess I mentioned that coal atom center, which is not a good idea for some, but
The research you do, yeah.
What's your proposal in your field? What do you think is for Sudan is best?
I tried to do a little reading in advance of this, so I'm primarily an optical astronomer, and optical observatories are usually go on top of mountains. There's actually not just any mountains though. Like you don't want the mountains in California, for example. We have lovely mountains here. They'd be a terrible place for an observatory because a big range of mountains. You get really bad weather because the weather fronts come over the mountains, go up, dump rain and snow on any country you're observing. So what you actually want is not the highest possible mountain, but a relatively isolated mountain. And apparently you guys have a nice volcano in the west that could be
Which is called Marah, Jabal, just as Marah mountain. We say Jabal Marah.
Okay.
It's Marah Mountains. Marah.
It's like
it means like one time. If it's one time, you fall in love with it.
It looked very beautiful in pictures. It reminds me of some of the
I've been there.
places
I've been
here.
there myself when I was a child.
So it'd be astronomy is moving in a whole bunch of directions. Some of the directions involve huge telescope projects that are billion-dollar scale things that obviously are only built on in particular locations. But some of the areas, and they look at one thing in enormous depth, but doesn't give it more than one galaxy or something like that. But a lot of astronomy also involves these kind of data mining projects where you want to do things like look at the entire sky and look for things that change, whether those are exploding stars or moving asteroids or aliens or something like that.
But if you look at the tomography of Sudan, we don't have mountains, a lot of mountains, and it's almost desert, and we don't have change in weather for months. You can have a clear sky.
Yeah, that's exactly. That's the sort of thing that goes well with these kind of monitoring projects. There's cases where there's things that we'd like to look at every minute for 6 months, and to do that you obviously need networks of telescopes all around the world.
Exactly. So I feel Sudan is one of the.
It's a place where you could place something.
So you can have free energy by building solar panels, and it's a desert. And the nice thing about the desert, this Sudanese desert, it has the longest river crossing. So you don't have problems with water. So you can pick any position at any point in that desert next to the river. You have free energy, and you have open sky.
Although dust is a problem, so with deserts you have to do something about it. But
that's one problem.
But not an unsolvable one. And even a small mountain that's in the middle of a desert is actually almost a perfect place for an observatory.
Which might be
yeah, exactly. So I want to find more. I'm actually curious enough to try and find more about it and to see there are packages people could send to places like this that would monitor the weather conditions over years, or see how much the turbulence in the Earth's air is distorting stars or things like that. It would be an interesting set of
So
measurements to make.
if there's someone with money or someone to be in touch with you,
Yeah.
also. So you hear that now, okay? There's an open invitation now to invest in Sudan.
Let's have a discussion about what one could do with a telescope.
Okay, excellent.
Modulo these sanctions and the export control laws, which are
Like
complicated things.
Thank you very much.
Thank you very much.
I have one
Yeah.
last before I start to but I want you, if after this little bit conversation,
Mhm.
I'm sure you can have a lot to say about Sudan. But what's if you want to deliver a message based on this 20 minutes to international community, including American people, what do you think you can tell them about just want a place to settle down using science, any place, not just Sudan? So what's your message?
I think what a good message for that is, and I'm not necessarily good at big, broad statements. I think these questions, like scientific questions, as I said earlier, are important, even if they're abstract questions. Still trying to understand our place in the universe is kind of why I get up and do this. But it's hard to worry about abstract questions when your country is unstable or desperately poor, and as you say, there's a huge amount of incredibly smart people in all these countries, as there are in every country. We're not taking advantage of this. We have a planet with huge, enormously complicated problems, and we need all the smart people thinking about it.
We have actually problems brain immigration in that
Yeah.
country. Like a lot of people live in the country.
It's a complicated problem for many countries to deal with. At least at the level of the world, taking advantage of smart people wherever they are, whatever country they're in, is better than nothing, but it would be better still if these people could stay and be smart in their own countries. And I don't know how to do that properly on any scale. But.
I forgot one question. I hope you forgive me for that. I wanted to ask you, how do you manage your resources? Like, how do you get fund for the research?
A mixture of funding. The university has provided some resources to me, as they do to new professors, and so that's helped set up a basic laboratory. I'm funded by the National Science Foundation and NASA for the astronomical research, primarily. As with every professor, that means I spend a lot of time writing grant proposals, but I do a reasonably good job of it. And then I'm very fortunate to have a bunch of really brilliant postdoctoral researchers like Andrew and Vanessa and others working for me. So actually, I just go to meetings. I just go to meetings and wave my hands around a lot and spend my time on stuff like that. I'm involved. I mentioned science policy, so I'm involved in review committees the U.S. has, where they try to decide how to do funding priorities for astronomy. So I spend a lot of my time helping think about where astronomy should be 10 years from now or 15 years from now, and how to spend our limited resources. And astronomy actually does a pretty good job internal to itself of setting out its priorities. Roger Blandford, who used to be the director of the institute here, chaired a committee 5 years ago that said this is what the next 10 years of astronomy should do. We didn't all get what we wanted out of that committee, but we all agreed that the process was good and that therefore we'll respect the answers. Come back in 10 years and reassess them.
Very nice. All right, then I thank you very much
You're welcome.
for giving me this
Fun to have
time,
these
and I'm
conversations.
very glad to talk to you.
Yeah,
It's very
nice to have you around here.